Imagine you have a powerful frontier language model that you can't fine-tune, either because it's behind an API or because retraining is prohibitively expensive. You still need to adapt it to a specialized domain like spreadsheet manipulation or document question answering. The standard playbook is to write a careful system prompt or skill document by hand, hoping the model follows your procedural guidance. But here's the awkward truth. Nobody really knows how to systematically improve these skill documents. You write one, you tweak it when it fails, you cross your fingers. There's no equivalent of gradient descent for the words in a prompt. That's the gap this paper tries to close. The authors introduce SkillOpt, which treats a natural language skill document as the trainable state of a frozen agent, and then borrows the discipline of deep learning optimization to update that document in a controlled way. The central idea is an analogy made operational. The skill document plays the role of the weights. A separate optimizer model plays the role of the gradient computation. A held-out validation set plays the role of early stopping, and bounded edits play the role of a learning rate. Think of it like running stochastic gradient descent, but where each step is a small textual edit to a markdown file rather than a numerical update to a tensor. Before getting into how it works, it's worth understanding what came before. One family of prior work, like GEPA and TextGrad, takes execution feedback and uses it to evolve prompts reflectively, treating language artifacts as optimizable objects. Another family, like Trace2Skill and EvoSkill, builds and evolves skill libraries from trajectory analysis, sometimes with failure-driven revision loops. These all have the right spirit, but they tend to either rewrite freely without any notion of a step size, or they lack a strict validation gate that prevents bad edits from accumulating. The result is unstable training. If one revision moves the skill document too far from the previous one, you lose the optimization history, and the next revision can't learn from what helped or hurt before. So how does SkillOpt actually work? At each training step, the frozen target model executes a batch of tasks from the training split using whatever the current skill document says. The system records full trajectories, tool calls, observations, verifier feedback, and final scores. Then a separate optimizer model, typically a strong frontier model like GPT 5.5, performs what the authors call mini-batch reflection. It splits trajectories into failures and successes, looks at small groups of each, and proposes structured edits to the skill document. The edits come in 3 flavors: add a new rule, delete an existing one, or replace one with another. By looking at mini-batches rather than single trajectories, the optimizer learns to spot recurring procedural errors rather than fixating on one-off mistakes. Now here's where the deep learning analogy gets concrete. The optimizer doesn't just dump every proposed edit into the skill. It ranks them by expected utility and clips the list to a bounded budget, say 4 edits per step. This budget is the textual learning rate, and you can schedule it with cosine decay, linear decay, or keep it constant. The candidate skill, with its bounded set of changes applied, then gets evaluated on a held-out selection split. Only if it strictly improves over the previous selection score does it get accepted as the new current skill. Otherwise, it's rejected. But rejection isn't waste. The rejected edits and the score drops they caused get stored in a buffer that future optimizer calls can see, so the system avoids proposing the same failed edit twice. This is negative feedback without any inference time cost at deployment. On top of all that, there's an epoch-wise, slow update that acts like momentum. At the end of each epoch, the system reruns the same training items under both the previous and current skill, sorts the differences into improvements, regressions, persistent failures, and stable successes, and writes a longitudinal guidance block into a protected region of the skill document that step-level edits can't overwrite. This captures durable lessons that survive across epochs rather than just within a single batch. There's also an optimizer-side meta-skill that summarizes which edit patterns worked and which didn't. But this stays on the optimizer side and never ships with the deployed artifact, keeping the final skill compact and portable. The empirical results are striking. Across 6 benchmarks spanning question answering, spreadsheets, document reasoning, math, and embodied navigation in ALF world, across 7 target models from GPT 5.5 down to small Quen variants, and across 3 execution harnesses including direct chat, the Codex CLI, and Claude Code, SkillOpt is best or tied best on every single one of the 52 evaluated cells. On GPT 5.5 in direct chat, it lifts the 6 benchmark average by 23.5 points over no skill. Spreadsheet bench jumps from 41.8 to 80.7. Office QA from 33.1 to 72.1. Even against an Oracle baseline that picks the best of 6 competing methods for each cell, SkillOpt is still 5.4 points ahead on average. And these gains come from remarkably compact artifacts. The final skill documents range from 379 to about 2,000 tokens, and most benchmarks reach their full gain after only 1 to 4 accepted edits. The transfer results are arguably the most interesting part. A spreadsheet skill trained inside the Codex harness transfers to Claude Code and adds 59.7 points over the Claude Code no-skill baseline, essentially matching what you'd get from training directly in Claude Code. A skill optimized for 1 model size transfers to smaller variants with positive gains, and a math skill trained on Olympiad bench transfers positively to Omni Math across 3 different model scales. The learned rules themselves, when you read them, are revealing. They encode procedural discipline that frontier models lack 0 shot, things like binding answers to specific visual regions in documents, materializing static values instead of relying on Excel formula recalculation, or maintaining a visited location ledger in embodied navigation to avoid loops. That said, there are real limitations. The training cost varies wildly. Procedural benchmarks like Office QA reach about 1 million training tokens per test point gained, while richer multimodal benchmarks like Doc VQA cost 46 million tokens per point. The method also assumes you have access to a strong optimizer model. When the authors swap in a target-matched optimizer that's the same scale as the deployed model, you still get meaningful gains, recovering 56 to 74% of the strong optimizer result. But the best results clearly depend on having a capable frontier model to do the editing. The validation gate is strict, requiring strictly greater scores, which is conservative and prevents drift, but also means edits with neutral or noisy effects are discarded. And the approach optimizes a single skill for a single domain. So building general agents would require either a skill library or some way to compose skills across domains, which the authors flag as future work. Now let's walk through some questions you might have after hearing all of this. First, why does the validation gate matter so much, and couldn't you just trust the optimizer's reflection? The validation gate matters because plausible textual diagnoses can still hurt the actual target model. The optimizer is reasoning about what should work, but until you actually run the candidate skill on held-out tasks with the frozen target, you don't know if its reasoning translates into behavior change. The ablation, where they remove the slow update and meta skill, drops spreadsheet bench from 77.5 to 55.0, which shows how easily an unconstrained editing loop can drift. The gate converts reflection into propose and test optimization, which is what makes the whole loop stable. Second, why does bounding the number of edits per step actually help? Couldn't a smarter optimizer make many good edits at once? In principle, yes, but in practice, unbounded rewrites tend to erase useful rules, introduce contradictory instructions, or overfit to whatever failure was salient in the latest batch. The bounded edit budget plays the same role as a small learning rate in numerical optimization. It keeps each new skill version close enough to the previous one that the optimizer's memory of accepted and rejected edits remains meaningful. If consecutive skills diverged wildly, the rejected edit buffer would be useless because you'd be optimizing against a different starting point each time. Third, the deployed skill ends up being just 1 to 4 accepted edits. Doesn't that mean almost all the optimizer's work gets thrown away? Yes and no. Most proposed edits do get rejected by the gate, but those rejections feed the buffer that informs later proposals, so the optimizer is effectively narrowing in on the rules that actually generalize rather than wasting compute. The compactness of the final artifact is a feature, not a sign of inefficiency. It means the deployed skill is interpretable, auditable, and small enough to drop into any system prompt without bloating the context, which is exactly what you want for a production adaptation layer. Now, how could these ideas apply to large-scale recommendation systems serving hundreds of millions of users? The most direct lift is in the policies that govern LLM-based components like conversational recommenders, query rewriters, and explanation generators. Today, those policies are usually hand-tuned prompts that get updated through manual A/B testing. SkillOpt's approach suggests treating each policy document as a trainable artifact, with offline trajectory logs serving as the rollout batches. Business metrics like engagement or conversion playing the role of the reward signal, and a held-out user cohort acting as the validation gate. The bounded edit budget is particularly important here because in recommendation systems, you can't afford unstable policy revisions that wipe out hard-won procedural rules around safety, freshness, or compliance. The cross-harness transfer result is also practically valuable. If you optimize a candidate ranking skill for one execution stack and find it transfers cleanly to another, you can amortize the optimization cost across multiple serving environments. And because the optimizer runs entirely offline and only the compact skill ships to production, this approach adds zero latency at serving time, which is the single hardest constraint in real-time ranking and retrieval. The pattern of 1 to 4 accepted edits encoding durable procedural knowledge maps well onto how recommendation teams actually evolve their systems in small reviewable changes rather than wholesale rewrites.